in the previous lecture, we finished test of hypothesis, and we now have chi-square tests. In this chapter, we talk about chi-square tests. Here, through this chapter, we just have three methods actually, but the last method is similar to the second method. Okay, the last methods have the same rule. We apply the same rule for the last two methods, but for the first one, it's different from the next two ones. Here we talk about apply the goodness of a test, and then we summarize data in contingency, and then apply the independence tests, and finally we have applying the homogeneity. In these two, we have the same rule. We apply the same rule in solving these two type of questions. And here, we have only one rule before. We have only one rule here. Okay? So we just have two rules through this chapter. It's only a little introduction. You can read it by yourselves. First, we talk about goodness of fit tests. Here, it's important. We have a table that you need to create from this given data. It's important to create that table. I'll tell you how to create the table. Now, we say, in throwing a dice, we have 6 possible outcomes. We either get 1, 2, 3, 4, 5, or 6. We just get these 6 outcomes in throwing a dice. لذلك قليل كانها شش أي تسكت معنا به. Okay? شش outcome here. Here we say, here we have a table. In this table, it says, in throwing or tossing a die 300 times. I'm tossing a die 300 times. When we have one die, we throw it or toss it 300 times. Among these 300 times that we toss the die, we obtained 45 ones. 45 times you get 1. And 52 times you get 2. 60 times you get 3. 58 times you get 4. 44 times you get 5, and 41 times you get 6. These are the outcomes of tossing a die 300 times. Okay? Here we say, we need to care about the dice if it is a fair dice or not. If it's a fair dice, the probability of obtaining any of the outcomes must be the same. Okay? The probability of 1 must be equal to probability of 2, must equal to probability of 3, must equal to probability of, and so on. Okay? All the probabilities must be the same if the dice is a fair dice. But if it's not fair, it must be given what's the rate of the probabilities. For example, it may say probability of 1 is 3 probability 2. Okay? Or probability of 6 is 2 probability of 5. Okay? ليه ذلك فين واتا شش عارفي كاه نبو من الله يعني سيركي ببشوي كراوت أجري أمدي أولى زياتر لا ونيا أجري كوت نسال أولى زياتر أو كات جوازة أجري كوت نسال أولى شد أوني كي أدري لبرسيان باشا. So if the dice is fair, what's the probability of obtaining 1 in throwing 1 dice? It's 1 over 6. It is the obtaining outcome over all the possibilities. Okay, we have 6 possible outcomes. So probability of 1 is 1 over 6. How about 2? How many twos do you have in a dice? 1. So what's the total of outcomes? 6. It's 1/6. Probability of 2 is still 1/6. How about probability of 3? Still the same. Probability of 4. Probability of 5. 1/6. And probability of 6 is still 1/6. Look, the probability of all outcomes must be the same if the dice is fair, is a fair dice. And be careful with that. The sum of all probabilities must be 1. The sum of all probabilities must be 1. It must not be, it must not exceed 1. If it exceeds 1, means you did a mistake somewhere. Look, the sum of these all probabilities must be 1. 1/6 plus 1/6 plus 6 times. It's 6/6, which is 1. It's the sum of all probabilities. The sum of all probabilities must always be 1. It must not be less than or greater than. That's it. It's talking about that. Here, in this chapter, we talk about hypothesis, which is the possibility of the given things. For example, here it says we have a fair dice. That means we think about that if we have a fair dice, the probability of all outcomes must be 1/6. So we name this by H0. We let this is to be the null hypothesis. What's the alternative hypothesis? If you have at least one of the outcomes with the probability doesn't equal to 1/6. That's the alternative hypothesis. Okay, we have these two hypotheses. And during solving the example, we get which of these is true. As the dice is a fair dice or not. We will have a relationship between chi-square test and chi-square from the table. Let me open the table also. Sorry. We need this table. For chi-square, we use it later on in solving the examples. Here we say if all probabilities are the same and it equals to 1/6, we name it by H0. Okay? Then we let H1 to be the hypothesis that if at least one of the probabilities is not 1/6. Okay? That's it. Then we will decide which of these is accepted and which is rejected. We just focus on H0. H0 accepted or not. Okay? We just focus on it like the previous ones. Okay, in the previous chapters, we did that. We said we could reject H0, we could accept it. We just said that. Okay? Then, here, in the examples or questions, these frequencies which are given are called observed frequencies. These are observed frequencies. Okay, these are observed frequencies. We need to find the expected frequencies. How to find the expected frequencies? We need to know the total number of the experiment. How many times did we throw the dice? 300. It's given. It's given that we have 300. And even if it is not given, the sum of all observed frequencies is the total number of the experiments. Okay? It's n. Here, the sum of these 45, 52, 60, 58, 41, 41, the sum of these all must be 300. Must be the same as the number of trials. Okay? So this is 300. We say it's n. N is the sample size, actually. It's the number of trials. N is 300. How to find the expected frequency for 1? It is the probability of 1 multiplying by 300. It is probability of 1 multiplied by the number of trials or multiplied by n. We say expected frequency for 1 is equal to, for any of them, let me write down general rule. For I, it is probability of I multiplied by n. That's all. It's written in the next slide, I think. It's written this rule. That's it. Okay. To find expected frequency for 1, we have given the observed frequencies for all the outcomes. This is O1, observed frequency for 1. This is observed frequency for 2. This is observed frequency for 3. This is observed frequency for 4. This is for 5, and this is for 6. We must have the expected frequency for each of these. Okay? So we need to find E1, E2, E3, up to E6. We say E1 is P of 1 times N. N is 300. What's P of 1? It's probability of 1. It's 1 over 6. We talked about this before. Probability of 1 is 1 over 6. Times 300, which is 50. That's 300 dividing by 6 is 50. Then E2 is probability of 2 is 1 over 6. How about N? N still 300 is 50. E3 is 50 equals to E4, E5, E6. Since the dice is a fair dice, we have the same probability for all outcomes. So the expected frequency for all outcomes the same. Means all of the expected frequencies here are 50. All of them are 50. That's how to find the expected frequency based on the number of data, number of trials times the probabilities. We get the expected frequency. We expect that in throwing a dice. I'm saying that if I throw the dice once, it's possible to get 1. The possibility of obtaining 1 is 1 over 6. How about in throwing the dice 6 times? It's 1. Okay? Then, how about obtaining 2? It's the same. 3, the same. 4, and okay? And so, the same. So how about throwing a dice 300 times? If in each 6 trials we get 1, let's say 5. 5 ones. In each 6 trials we get 5 ones. How many 5s do you get in throwing 300 times? We get 50. Okay, that's it. Yes, talking about this, these are the expected frequencies, and the observed frequencies are those which are given and must be given. Observed frequencies must be given. We don't know what we get in those trials. Okay, so it must be given, but we could get the expected frequencies from the probability of each outcome multiplied by the number of trials. Here we use this rule. You should memorize this rule. You should memorize this rule. We say chi-square test. Chi-square test is the sum of OI. We know what are I's. minus EI all squared, and then dividing by EI means it is, if you have, let's say, 6 outcomes, if you have 6 different outcomes, means you have O1 up to O6 and E1 up to E6. It is O1 minus E1 squared over E1 plus O2 minus E2 squared over E2 plus O3 minus E3 squared over E3, and so on up to the number of outcomes. In throwing a dice, we have 6 possibilities. So we get O1 minus E1, O2 minus E2 up to O6 minus E6. We find this. So it just depends on the expected frequencies and the observed frequencies which are given in the exam. We just focus on these two. If you have these two, we could get the chi-square test. And then we need to find chi-square from the table. Check if there is anything that we left. No, it's okay. Now, this is the chi-square test, and this is chi-square that you could get from the table, this table. Let's look for chi-square. This is T, this is chi-square. This is chi-square, okay? That's it. This is chi-square table. From this table, we could get this part. You say it is chi-squared of alpha. Alpha must be given. It's the significance level. Alpha, then K minus P minus 1. K is the number of possible outcomes. It's the number of possible outcomes. And throwing a dice, it's 6. Okay? And P is the number of unknown parameters. Okay? It's the number of unknown parameters. Here, there is no examples actually about having unknown parameters. But if there's something unknown in the example, let's say we have 2 things which are unknown. We say P is 2. But here, we have no any examples that we have unknown parameters. Here, P is 0 here. As we have no unknown parameter, we say P is 0. P is the number of unknown parameters, then minus 1. For this example, K is 6. In the example, there is nothing which is unknown. It's 0. Then minus 1. It is 5. That means we need to find chi-square of alpha and 5. Alpha must be given. And we have alpha, and we also have 5. It's the level, degree of freedom. This is the degree of freedom. This is called degree of freedom. We have degree of freedom. And if alpha is given, we could get the result from the table. From this table, we could get. These are the values of alpha, and these are values of these are degree of freedom. Okay, 5, as we found that it's 5, then we look for the value of alpha here horizontally to get the result. It's for the example if you have tossing a dice. So you should know this rule. We say if the chi-square test, this chi-square test, and the right-hand side of the inequality is the chi-square that you get from the table. We say if the chi-square test is greater than chi-square that you get from the table, we reject H0. We reject the hypothesis which is given in the example. as in this example, if it says, if we have a fair dice and we get this table in tossing the dice 300 times, okay? In this case, as it says, if the dice is a fair dice, this is the hypothesis which is given in the example. We always name this by H naught. It says the dice is a fair dice. What's the opposite of this statement? If the dice is not a fair dice, okay? That's H1. Okay? In the case if chi-square test is greater than this, if chi-square test is greater than this number that we get from the table, we reject H naught. That means we say that the dice is not a fair dice. It's not a fair dice. Okay, so H naught is not accepted in this case. If the chi-square test is greater than chi-square from the table, we say we reject H naught and we accept H1. And we said H naught is that the dice is a fair dice. We reject this statement. We accept H1 means the dice is not a fair dice. If this is true, if this inequality is true, we say that. What if it is not true? We say we accept, or we cannot reject H naught. Means the dice could be a fair dice. Now let's solve this example. The one which is given, we solve. Okay? We need to make this table. We need to make this table to solve it easier and don't get mistake. These are the observed frequencies which are given. This is O1, O2. Write down in order as it's given in the example. Then find the expected frequencies for each. For one is this one, look, it's O1. So you must find E1 here. At this probability of 1 times the number of trials, which is 1/6 times 300, it's 50. Then for others, for 2, for 3, up to n. In the same order as O. This O1, O2, up to n. Let's say if this is O2 and this is O3. Even here must be 3 and 2. It must be in the same order. Okay? We say, we need to find this one. We need the sum of these, which is the chi-square test. Chi-square test is the sum of OI minus EI all squared dividing by EI. This is the rule for finding the chi-square test. We say it is 45 minus 50 squared dividing by E1. That's E1. It's the rule. This equals to O1 minus E1 squared dividing by E1. This one is O2 minus E2 squared dividing by E2. And so we find this all. After calculating this, as you see, here we got 0.50, this 0.08, this is 2, 1.28, 0.72, 1.62. We say the chi-square test is this one plus 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 this one. That means it's the sum of these numbers. It is the sum of these numbers. Okay? It's easier to calculate to get the result. Okay? If you do it step by step and make that table, it's easier to get the result. Here, chi-square test is the sum of these. It's 0.50 plus 0.08 plus 2 plus 1.28 plus 0.72 plus 1.62. That's it. Find the sum of these. This is the chi-square test. What else should we find? Chi-square from the table. Chi-square from the table. But here we must have, look, it's used as 0.05 alpha. Alpha must be given, okay? I think it's given somewhere here, but don't care about that. Okay. This is chi-square test. Let's see what's the result of chi-square. It's 6.20. This is chi-square test. Then we need to find chi-square of 0.05 and k minus p minus 1. There is no any parameter, a noun parameter here. Everything now means p is 0. What's k? K is the number of different outcomes. It's the total number of outcomes. How many outcomes do you get in tossing a dice? 6. So this is 6. Minus 1 is 5. So it is chi-square of 0.05 and 5. Now we return to the table to get this value. To get this one, we need to return to the table. Let's return to the table. It is 0.05, it's 4 alpha, and 5, it's V. This is 5. Then 0.05, that one is. It's 11.07. This is 11.07. Then we say chi-square of 0.05 and 5 is 11.07. Then we compare this one with the above result that you get from the table, from the chi-square test. If yes. Yes. It must be given. It must be given. It's alpha. It's alpha. It's the significance level. Let's look at the next example. That's it. Look at the next one. That's it. It must be given. Or it's given as a percentage. It may say, or let's say 5% significance level. Means this is 0.05. Okay? It's 0.05. It's either given as a decimal number or a percentage. Okay. Here, this is the chi-square from the table. It's 11.07. And we already found chi-square test. Chi-square test is 6.20. Which one is bigger? This one. We said if chi-square test is greater than chi-square of alpha k minus p minus 1, if this is greater, in this case, we'll reach recording. Okay. For H note, we said the dice is a fair dice. Okay. H1 states that the dice is not a fair dice. We said if chi-square test, which is 6.20, is greater than the chi-square from the table, which is 11.07. Is it true? Is this statement true? Is 6 greater than 11? No, it's not true. This is not true. Means we cannot reject. If it's true, then we reject H notes. But here, it's not true. This statement is not true. Means we cannot reject H notes. So you have no enough evidence to say that the dice is not a fair dice. We could say the dice is a fair dice. It's not a fair dice, not a fair dice. Sorry. I said we have no enough evidence to show that the dice is not a fair dice. So you could say the dice is a fair dice. We accept H naught. H naught states that the dice is a fair dice. That's it. That's all. لا كي بي صفر اگر هاتو هموش تكن زانداو هیچ نزاندايقن هم اويك هي اويك بينيوم همي زاندا باشا لا انا خوي بلا اگر فلانش نزا فلانش الناون بين بوندوش بلا الناون خوي بلا او كاتا دو دعني لجيبي باشا اقعد الموضوع. Look at this example. Here we have another example. It says the authority claims that the proportions of road accidents occurring in this country according to the categories. We have these categories, okay? User attitude, mechanical fault, insufficient signboard, it's 3, and fate is 4. We have these 4 categories, means we have only these 4 outcomes. We have 4 outcomes. So let's write down all the given information. K is 4. That's it. Then, and their probabilities are 0.60. It's for the first one, as at the end it says respectively. So it is for the first one. Probability of A is 0.60 means 0.6. It's 60 over 100, which is 0.6. Then probability of M, probability of M is 20%. So probability of M is 0.2. Probability of I in order, okay? Probability of I is 15%. So probability of I is 0.15. And then fate, the probability of the last one is 0.05. 5%, which is probability of F, is 0.05. These are the probabilities. Look, in a dice, it may not be given. It may not given, okay? Because we know it's 1 over 6, 1 over the number of outcomes. But if they are different, it must be given like this, okay? All the probabilities are not the same here. Even if the dice is not a fair dice, the probabilities must be given like this, okay? Now we have the probability of each outcome. It says, a study by an independent body shows the following data. We have M under 30 times. So A, M 35 times, I 30 times, and F 5 times. And the total number of trials is 200. This is N. N is 200. These values which are given, what are these? What are these frequencies? It's observed frequencies. This is O1, OA, this is OM, this is OI, and this is OF. What should we find? We need to find the expected frequencies. Okay? Let's find the expected frequencies. We already have the probability of each outcome. We say expected frequency for A is probability of A times 200 times n. Okay? Let me write down n times n. N is 200, is the total number of trials. This equals the probability of A is what? It is 0.6 times 200. We get E1. For we get EA. How about EM? We multiply 0.2 by 200. Then for EI, we multiply 0.15 by 200. And then for this one, for F, EF, expected frequency for F, we multiply the probability of F, which is 0.05, by 200. We get all the expected frequencies. We now have observed frequencies and expected frequencies. We now ready to make the table. Okay? That's the table. We could make the table. These are the observed frequencies which are given. And here we found the expected frequencies. What we need to calculate, we need to calculate this column minus this column squared dividing by this column. Okay? It's O minus E dividing by E. We do that at each row. Yeah, this is OA minus EA. This is squared over EA. And this one is OM minus EM. This is squared dividing by EM. And this one is OI minus EI dividing by EI. This is squared. Only the numerator is squared. And this one is for F. It is OF minus EF dividing by EF. And numerator is squared. The sum of these is the test, is the chi-square test. Sum of these is the chi-square test. We found these one by one. We add these all, and the chi-square test is the sum of these. This is the chi-square test. And we need to find the chi-square from the table. There is no anything unknown. So there is no unknown parameter. And we know that we have only 4 outcomes. A, M, I, F. We have these 4 outcomes. Means K is 4. See, chi-squared of K is 4 minus P is 0, then minus 1, which is chi-squared of 3. Chi-squared of 3, sorry, alpha, we haven't written down alpha. Let me write down alpha first. Say chi-squared of alpha and K minus P minus 1. P here is 0, and alpha is given. As you see in the example, it's given. That's it. It's 0.05. It must be given. Even if it's not given as alpha equals to that amount, it might be given as for example, let's say 5%. Yeah, it may be given 5% significance. Okay, level of significance. It may be given as 5% of level of significance. It may not be given as alpha equals to that amount. It may be given like level of significance, percentage of level of significance. You should know that means alpha. That's it. Then we say it equals to chi-squared of alpha is 0.05. Then K is 4, P is 0, minus 1. It is 3. Now let's look for this value in the table, 0.05 and 3. This is 3. Then 0.05 is here. 7.81. This is 7. Now, if the chi-square test is greater than this amount, we say we reject H0. What was H0? H0, look, let's read the question carefully. It says the authority claims that the proportions of road accidents occurring in this country according to the categories. That means all the accidents are because of one of these things. Okay, according to these things. This is not. H0 is the hypothesis that the car accidents are all according to these 4 things. What's the null hypothesis? I mean the alternative hypothesis, or H1. H1 is that if all the car accidents are not according to these 4 things. Okay? كاتالي همو روداوة كان روداوة تنبيل كان بوي أمانوي. Okay? على تنها بوي أمانوي. This is H0. What's H1? If all the accidents are not according to these things. That's H1. That means if the chi-square test, we found chi-square test, that one. If this is greater than that amount, we refuse H0 or we reject H0. Okay, H0 states that all the car accidents according to those 4 things. Okay, but in this case, we cannot reject H0 because this is not greater than that one. If 3.958, if this one was the chi-square test, is greater than 7.81, then we say we reject H0. Sorry, this is greater. Must not be less. If chi-square test is greater than this one, we reject H0. If not, we not. So we conclude that we accept H0 and conclude that we have no evidence to reject the claim. Claim states that all the car accidents are according to those 4 things. That's it. Now let's take a break for 10 minutes, then we'll be back. We now have another example. It says the number of students playing truancy in a school over 200 school days is shown below. Number of truancy 0 in 12 days, 1 in 32 days, 2 in 45 days, 3 in 50 days, and 4 in 35 days. So we have 0 truancy in 12 days. We have more than 200 days, more than 200 school days. Okay. The number of truancy, if there is no truancy, okay, if no one played truancy, we have only 12 days. In 12 days, no one played truancy. Only one truancy game in 32 days. 2, 45 days. 3, 50 days. 4, 35. And for greater than 5, more than 5 truancy games, we have 26 days. In 26 days, we have more than or equal to 5 truancy games played. Okay? Look, we have given that for 0, we have 12. For 1, we have 32. For 2, we have 45. For 3, we have 50. For 4, we have 35. And for greater than 5, we have 26. How many outcomes do you have? Possible outcomes. It's either 0, 1, 2, 3, 4, or greater than or equal to 5. Means we have 6 possible outcomes from 0 to greater than or equal to 5. And these values which are given, which is the number of days, represents the observed frequency for each of them. For 0, the observed frequency is 12. For 1, the observed frequency is 32. For 2, the observed frequency is 45, and so on. Now, we have that K is the number of possible outcomes, which is 6. Number of data, it's 6. Then, the observed frequencies are given. We have given the observed frequencies, which are 12, 32, 45, 50, 35, and 26, respectively, for 0 to greater than or equal to 5. We have these observed frequencies. Then, we need to find the expected frequency. We need to find, first, we need to find all the expected frequencies. Then, we make the table. What are the expected frequencies? Let's read all the question first. If X is a random variable representing the number of students playing truancy per day, test the hypothesis that, this is the hypothesis, it's mentioned, the hypothesis. X follows the Poisson distribution with mean 3 per day. This is the hypothesis which is given. So this is H0. The hypothesis which is given in the context, we name it by H0. So what's H1 here? H1 says that X doesn't follow the Poisson distribution with mean 3. Okay? That's the H1 hypothesis. We now have what hypothesis? Alpha is given. Now, we have Poisson distribution. In Poisson distribution, mean denoted by lambda. Mean denoted, you studied this in the beginning of this course. Okay? Lambda is 3, as it is Poisson distribution. So mean denoted by lambda. What's the probability for a number? We have a rule for finding probability of a number in Poisson distribution. It's different from the other distributions. You say probability of, let's say, x to be little x is equal to, this little x represents 0, 1, 2, 3, 4, and greater than or equal to 5. Okay? Is equal to e to the power minus lambda minus mean times lambda to the power x dividing by x factorial. This is the rule for that. Okay? This is the rule for finding the probability at a value in Poisson distribution. أبي أمتى أخوان Now, we need to find the probability for each of the outcomes. And then we multiply the probability of each outcome by the total number of trials, which is 200, to get the expected frequency for each outcome. We need to find E naught. E of 0, I mean E of 0 is probability of 0 times n. N is the total number of trials, or the total number of observed frequencies. The total number of observed frequency is n. That's 200. That's given. That's 200. Even if it's not given, find the sum of these, you will get it. Then, what we need in the finding of expected frequencies, it's for E naught, E of 0. How about E of 1? It's probability of 1 times n. E2 is probability of 2 times n, and so on. How about probability of greater than or equal to 5? It is, sorry, E of greater than or equal to 5 is probability of greater than or equal to 5, greater than or equal to 5 times n. We need to find these all. After finding these, then we can make the table. Let's first find them. It should be, yeah. It's given. Even the sum of these should be 200s. Okay. Now we have n, and we need to find the probability of 0, probability of 1, probability of 2, up to probability of greater than or equal to 5 by using Poisson distribution. In this case, we must use the Poisson distribution for finding the probabilities. As it's given, X follows the Poisson distribution. This is the hypothesis which is given in the context. So this is not. How about H1? We say X doesn't follow Poisson distribution with mean 3. That's the alternative hypothesis. Now, let's find probability of 0. Probability of 0, lambda is 3 for all of them. Lambda, it's given. It's 3 for all of them. Probability of 0, of capital X to be 0, is equal to, we use this rule, okay? This X and this one, what's in the denominator, both are this little x, okay? For 0, it is e to the power lambda minus lambda, which is minus 3. It's e to the power minus 3 times lambda, which is 3 to the power 0, the power x, dividing by 0 factorial. What's 0 factorial? It's 1. Yeah. So we get 3 to the power 0 is 1. And denominator is 1. We get 1 over e to the power 3. Calculate this. You'll get a value. And the value is given here, which is this one. This is probability of 0. How about probability of 1? Probability of capital X to be 1 is equal to e to the power minus 3, it's always 3, lambda is always 3, times 3 to the power 1, dividing by 1 factorial. 1 factorial is 1, denominator is 1, and it is 3 over e to the power minus 3. This is the value. And then for 2, probability of 2 of X to be 2 is equal to e to the power minus 3 times 3 to the power 2 dividing by 2 factorial. 2 factorial is 2. It's 2 times 1. It's 2. So we get 3 to the power 2 is 9. أما 2 أنا كي سالب أبين زيادة همیشه بكبير مثلا زائد بين. It's 9 dividing by 2 factorial is 2 times e to the power 3. Calculate this. You'll get this value. And then for 3, for 4, for greater than or equal to 5. Let's see how to get this one. We say the sum of all probabilities must be 1. The sum of all probabilities must be 1. We already found probability of 0, 1, 2, 3, 4. How to get the probability of greater than or equal to 5? We say probability of 0 plus probability of 1 plus probability of 2 plus probability of 3 plus probability of 4 plus probability of greater than or equal to 5. These all of them must be 1. How to get the probability of greater than or equal to 5? We move these all to the other side. We get 1 minus the probability of all the others. Is it? We get probability of greater than or equal to 5 is 1 minus the sum of probability of, let's say, I from 0 to 4. Okay? It's 1 minus probability of, let me write down in detail. We found probabilities from 0 to 4. To get the probability of greater than or equal to something, we say all the probabilities, the sum of all probabilities must be 1. Probability of 0 plus probability of 1 plus probability of 2 plus probability of 3 plus this must be 1. How to get this one? Only this one is unknown. We already found these all. How to get that? We move these to the other side. And we get probability of greater than or equal to 5 is 1 minus the sum of all the other probabilities. We find the sum of this. And then we say probability of greater than or equal to 5 is 1 minus the sum of this. Okay? We get the probability of greater than or equal to 5. That's it. Now we found the probabilities. After finding the probabilities, what should you find? The expected frequencies. The expected frequencies. We need to find E0. This expected frequency for 0. This equals to the probability of 0 times n. We said n is 200 here. It's the sum of these all observed frequencies. It is this one times 200s. This is E1, E0. And E1 is this one times 200s. E2 is this one times 200s. E3 is this one times 200s. This E3. This is E4. E5 is this one times 200s. We find all the expected frequencies. We now have observed frequencies and expected frequencies. We now can make the table. These are observed frequencies which are given. And these are, look, it's probability at 0. And this 200, which is multiplied by 200s. And this probability at 1 multiplied by 200s. That's what I said now. These are the expected frequencies. Okay? Don't round them. Okay? Don't round them. For this one, let's say it's 10. It's not 10. It's 9.96. Write down as it is. Now, we could find OI minus EI squared dividing by EI. This column depends on this one and this one. We have them both. This one minus this one squared dividing by this one. We get this back. Now we get this column for OI minus EI all squared dividing by EI. From this column, we can get from this column, we could get the chi-square test. Chi-square test is the sum of these values, only the sum of these. Okay? It's 0.42 plus 0.15 plus 0 plus 0.60 plus 0.06 plus 3.24. The sum of these all is the chi-square test. Okay, that's it. This chi-square test is 4.47. Then we need to find chi-squared from the table. The rule is we say chi-squared of alpha. Alpha must be given in the example. It's given here, which is 0.01. Okay. It's chi-squared of alpha, then k minus p minus 1. K is the number of possible outcomes. We either get 0, 1, 2, 3, 4, or greater than or equal to 5. So you have 6 possible outcomes. K is 6. P, there is nothing unknown. Even it doesn't say there is a parameter, there is an unknown parameter. So it's 0 minus 1. 6 minus 1 is 5. We get chi-squared of 0.01 and 5. Let's look for this value in the table. 0.01 and 5. This is 5. 0.01. This one is. It's 15.09. 15.09. It's nothing here actually. That's it. Vale, search picture. If it is greater than this one, then we say we reject. Now, we found them both. Chi-square test from the table, that we create, and chi-square test from the given table, from this one. Okay? So this is chi-square that we get from this table, and chi-squared from this table. We compare them. If chi-square test, if this one is greater than this one, we reject H naught. What was H naught? Let's return. You need to write down the statement of H naught and statement of H1 during in solving the questions, even during exams. And look, it's like this. You need to write down all the given information like this. So, okay, H naught, H1, and then start to solve it. Okay. Here, H naught is X follows Poisson distribution with mean 3. We cannot reject this one because chi-square test is not greater than that chi-square that we get, which we get from the table. Okay, this is 4.47, and chi-squared from the table here is 15.09. This is 15.09. Is 4.47 greater than this? No. We are unable to reject the hypothesis, the null hypothesis, or H naught, which is X follows the Poisson distribution with mean 3. That's it. It's not accepted, and you conclude that no evidence to reject this evidence. Yeah. This hypothesis. Vale. Circa. Emily probability يك زائد probability دو لبعدها زائد كده باشا زائد probability سه زائد probability 4 زائد probability 5 اگر ما نزن دابت probability 6 نزن دابت كويهم يعني بكاتا شنا يك شون probability شوش بسمو أما أنا زان داون كويهم يعني قريب أنا كاتا 0.8121 شيكين أما أبين أودي يبقى ناقص يك ناقص كوي probability يعني ليش هون we said it is 1 minus the probabilities of this one, this one, this one, this one, and this one. You find the sum of these and you push to the other side. It's about this example. بلام لكاتي امتحان سيكن ليرة في سلسلة أمشي شوازي نسينا كده إيش نوتو إيش نوت بنوسن امتحان باسم كردوا نموتو أمشي باشا بس ممكن نوم ما ولا سيتاو ليرة أما given أما إيش نوتا إيش نوت أويك أخوي إياه ده بس يعني H1 دجيا this H1 if you know what's H naught H1 is easy to write down it's opposite to H naught then make the table okay that's it and even for this example it's the same you have this example in this example it says it's believed that look it says it's believed that the IQ score of all adults follow the normal distribution with mean 110 and standard deviation 10. This is the null hypothesis. Okay? And it says it's believed that this one is true. So this statement is null hypothesis, H naught. What's the alternative hypothesis? If that statement is not true, means if the IQ score of adults doesn't follow normal distribution, if it doesn't follow normal distribution, this is the null hypothesis. If you know what's the hypothesis, I mean H naught, you know what is H1. The score of IQ test given to 250 adults are summarized below, where X represents IQ score. X represents the IQ score. For those who got less than 90 in the IQ test, we have only 2 adults. For those who got IQ scores from 90 to 100, we have 30 adults. And 85 adults got 100 to 110 in the IQ test. Then 90 adults got 110 to 120 in the IQ test, and so. Okay? Test above. Believe at alpha to be 0.05. سير كليرة تشتكي أم statement يدوم تنها معلومات يعني. بلان أول سر تشيت يا hypothesis يعني. Okay? أبي بزاني كم hypothesis كم statement. In the above one it says it's believed that the IQ score of all adults follow normal distribution. This is the H naught. What's H1? We say it's believed that the IQ score of all adults doesn't follow the normal distribution. This is H1. It's opposite to H naught. You need to write down both H naught and H1 first, and all the given information. And then, look, we have given that mean, which is mu. In Poisson distribution, mean denoted by lambda. But in normal distribution, mean denoted by mu. And standard deviation is sigma. It's sigma. What's variance? Variance is sigma squared. Okay? variance is sigma squared. It's standard deviation squared. We have 250 adults. This is n. This is n. Alpha is given also. We have given these information. Write down them. Then, what should we find? These are the observed frequencies. These are the observed frequencies. We need to find the expected frequencies. We need to find the expected frequencies. The expected frequency, expected frequency for x to be less than 90 is probability of x to be less than 90 times 250 times n. N is 250. Then expected frequency for between 90 and 100, 90 is equal to probability of x to be greater than or equal to 90 and less than 100 times 250. And so, okay, we follow this to get all expected frequencies. But here, this probability need to be obtained from the normal distribution. In the previous example, we used Poisson distribution because it was given that it follows the Poisson distribution. Okay, but here it's given that it follows the normal distribution. You need to use the rules in normal distribution to get these probabilities. In normal distribution, we always use Z table. Okay, we always use Z table. Yeah. Here we say, let me explain this one here. That one. When we say the probability of x less than 90, let's say it's 90, 90 less than this area. We need to standardize this. X is less than 90. We need to standardize this and then find it from Z table. Okay, how about the second one? As it says, between 90 and 100. Sorry, before we do that, let's standardize and then do this. Okay, to standardize, we use this rule. We say Z is equal to capital X minus 110 over 10. This 10 is the standard deviation. This is mean. This is mean. We say standardization of normal distribution. We say capital X, it says less than 90, we choose to be X, okay? X minus mu over sigma. This is Z. We standardize this, we convert it to Z because we have no any table for X. We have a table for Z. The table for Z is this little table. This one is. Let me check, sorry. No, sorry, we return to normal distribution, not that one. We use normal distribution. Let me find the normal distribution table first. Standard normal distribution, this one is. This is the normal distribution. This also normal distribution. These two tables belong to normal distribution. This one for the negative values of Z, and this one for positive values of Z. But these all are for what? It's probability of Z to be less than an amount. Okay? It must be less than. What if it is greater? 1 minus that amount less than. Okay? We do this. We need to find Z first for each or at each of these. For the first one, it's 90. So Z for 90 for X to be less than 90. You say probability of this is probability of Z is less than capital X minus mu over sigma. X here is 90, is it? It's 90 minus 110 dividing by 10. Okay? And this equals to probability of Z to be less than 90 minus 110 is minus 20. Dividing by 10 is minus 2. It's already less than. We can get from the table directly. Okay? Probability of Z is less than minus 2. We look for minus 2 in the normal distribution table. Cumulative standard normal distribution or cumulative standard normal distribution. We have these two tables. For minus 2, let's look for minus 2. This is minus 2. It's on that row. And which column? Which of these should we choose? We look at the columns. Which one is 0, 0? It's only minus 2. It's minus 2.00. Is it? It's only minus 2, so it's minus 2.00. We look for 0, 0. This one is. It's the last column because you have no decimal points. We have no decimal points, so we go through this row to get to the final column. This one is. It's 0.22. It's 0.227. This is the probability of Z to be less than negative 2, which represents the probability of this one. Okay? It represents the probability of this one. How about the second one? Let's do it here. We have probability of X between less than or equal to 90 and greater than or equal to 90 or less than 100. This equals to what? It equals to probability of Z is equal to this value. Okay? Z greater than that value. See, Z greater than or equal to 90 minus 110 over 10. And here we get 100 minus 110 over 10. Okay, we just replace X by the boundaries. By 90 and 100. This is the rule. This one is Z. Mu is given, which is 110. Sigma is given is 10. Look, that's it. This is sigma, and this is mu. Now we find this. It's probability of Z is greater than or equal to negative 2 and less than negative 1. It's between negative 2 and negative 1. How to find it? It's less than negative 1. It's okay, we can find it. How about the greater? Let's use the graph. For this one, it's easier to use the graph. This is normal distribution. Okay, Let's say it's 0. We don't need 0. We have -1 and -2. Later, we need to find the probability of this area. We need to find that area. Okay? How to find it? It is its probability of z to be less than -1. Where is it? It is from -1 to left. These all. It's for less than -1. It is this area. This green one is probability of z to be less than -1. What should you subtract from this to get the yellow region? Probability of z less than -2. Is it? Look, probability of z less than -2 is this one. From the green one and the brown one, if we subtract the brown one from the green one, what we get? The yellow part. Is it? So it's how to find the probability of z to be between two values. Then we say it is probability of z to be less than -1 minus probability of z to be less than -2. We could get these both from the table. We could get these both from the table. And we subtract them, we get the results. Okay? Take no area. Okay. Now we have probability of -2. How about -1? Look for -1 in the first column. As you have no decimal points, so we use the last one. It's 0.158. Minus 0.227. Find it. Vale? Emma. Above this one? Just over here. We use this one. This one is, I think, probability of x to be between 90 and 100. We need to standardize. Those between. Yes. Yes. It could be between -2 and negative. Because it's greater than -2 and less than negative. بس جمال ما هي لا يصير كده يصير real line. Look at the real line. This is 0, -1, -2, -3. Between -1 and -2. That's it. Okay? Between them. So now we do the same for all. We do the same for all. Okay? To get all the expected frequencies. It takes time actually to find them all here. These are the probabilities. These are the probability of all of them all. Okay? Probability of greater than 2. That's 1 minus probability of less than 2. This one, only this one is different from the previous ones. It is 1 minus probability of z less than 2. That's it. You could get probability of z less than 2 from the table and subtract it from 1. You get the result. These are the probabilities. From these probabilities, we could get the expected frequencies from this one. E of less than 90. E of less than x less than 90 is equal to this probability times this probability times n. N is 250. And probability of this one, so expected frequency for this one is this amount times 250. Expected frequency for this one is this amount times 250. It's for all. We find their expected frequencies. These are them. These are the expected frequency. حتى استنها frequency expected frequency ما ندوسيون. Up to now, we just worked for finding the expected frequencies. And from now, it's easy. It's only calculating chi-square test and chi-square from the table. Table is a table normal distribution. Bale. إذا expected frequency bale. But I'm زيادة أبي بشكل يكسر باش معنا كلا table كأن جات عندنا. Okay. If you have something like this, P of Z to be greater than 1, you cannot get this value from the table directly. What we do, we say it is 1 minus probability of Z less than 1. It must be less than always. Okay? Then we can get it from the table. We now have observed frequencies and expected frequencies. We could obtain this one. We can calculate this one. Observed frequency minus expected frequency at each level squared, dividing by expected frequency at that level. We get these values. And the sum of these values is the chi-square test. The sum of these is the chi-square test. This is chi-square test. How to get the chi-square from the table? Number of data. 1, 2, 3, 4, 5, 6. So K is 6. P, there is no unknown things. So it is P is 0. So chi-square from the table for alpha. Alpha is given. What's alpha? It's 0.05. It's chi-squared of 0.05. And K minus 1. K minus P minus 1. P here is 0. So we just say K minus 1. K minus 1 is 5. Let's return to the table of chi-squared. This is chi-squared. Yeah. This is chi-squared. 0.05 and 5. That's 11.07. Okay. 0.05 and 5. That's 11.07. This one is the chi-square test. If this chi-square test is greater than this, like this, not good less than, it's greater. If we reject H naught, if chi-square test is greater than the chi-square which you get from the table. Is this one greater than that? No. So we cannot reject the hypothesis. So it follows the normal distribution. It follows the normal I-score. There is no evidence to support this statement. To support IQ test doesn't follow the normal distribution. So it means we accept H naught and we say the IQ score follow normal distribution with mean 110 and standard deviation 10. That's it. بلا تيبلو بيت. That's بس بۆ دۆزینی پرۆبابلیتەکان ئێمە ستاندەرایزیەکەین بۆ دۆزینی پرۆبابلیتەکان ئەو ژمارانەیە کە لە زیێ تا دەستمانەکەوێت لە هیچ شوێنێکدا بەکار نایەت تەنها لە پرۆبابلیتەکە بەکارهێنین بۆچی ئەویش تەنها بەکارهێنە بۆ بەکارهێنەر لەناو تەیبڵەکەیە چونکە ناو تەیبڵەکە و ژمارە گەورانیتیانە وازان ناقس سێ و ناقس تا ناقس چواریش وازانتیانی با برێکی وەرگرین okay. We now have another test, which is the second topic in this chapter. It's independence test. Here, if you look at this table, which is given, we have 7 students. You have 7 students. Student A, B, C, D, E, and F. Then, here, it says the spectacled wearing glass or not, okay? Student A wears glasses. Student B doesn't wear glasses. Student C wear glasses. D wear glasses. E doesn't wear glasses. F doesn't wear glasses. And F, G wear glasses. Okay? Then, the result in a subject, in a module. The result of student A, which wear glasses, is excellent. The result of student B in that module, student B doesn't wear glasses and got excellent. Student C wear glasses but got good. D wear glasses, got excellent. E doesn't wear glasses, got no, good. F doesn't wear glasses, got good. And finally, student G wear glasses and got excellent. Okay? We have 2 categories here. Wearing glasses or not. Okay? And their grade. Their grade is excellent or good. We have only 2 options in their grades. It's either excellent or good. If we make this to a table of data, we say we have horizontally, let's say it's for that to wear glasses or not, be spectacle or not. Okay? Bespectacle. Bespectacles. Okay? Then this is their grade. This is their grade. Sorry. We have 2 options for bespectacles. It's either yes or no. Is it? It's yes or no. And for grades, for let's say marks. In the marks, we have 2 options. It's either excellent or good. Okay? I'm just writing down EX for excellent and G for good. Now, to fill this table, what we do? We need to count the number of those students who wear glasses. Look, horizontally, it's wearing glasses. Okay, it says, how many students wear glasses? Let's count here. 1, 2, 3, 4. We have 4 students who wear glasses. Okay, and how much among of them, how many of them got excellent? 1, 2, 3. So we write down 3 here. Okay, wear glass and excellent, we have only 3 students. And wearing glass and got good, we have only 1. This one. Then for doesn't wear glasses, we have 1, 2, 3. We have these 3 students who doesn't wear glasses. How many of them got excellent? Only 1 of them. Okay, 1 of them got excellent. How many of them got good? 1, 2. Okay, it's important if we have given a context to create this table, to create the table. But in most of the examples, the table is given, even in exams. I looked at many of the past papers and the tables are all given. Okay, even if the table is not given, it's how to make the table. We work on this table for solving the question, for answering the questions. Okay, here, as you see, we have these 4 numbers: 3, 1, 1, 2. We write down this in a matrix. This is for yourselves. You don't have to write down that matrix in the solution. Okay, even if you use this matrix, clean it. Okay, then we say, what's this element in a matrix? This element is 1, 1. Is it? It's 1, 1. How about this one? 1, 2. Its location, the indices here is 1, 2. How about this one? 2, 1, 2, 2. Okay, so what about if we say مثلا تخوين دوا vale? Okay, you used MATLAB programs for writing a program about array. Is it about array? Array MATLAB? Okay, when you say if you have A be a matrix, A of 1, a column, what's that mean? 1 and a column. This means that is first row. It's first row. Is it? It's first row. How about A of and 1? It's first column. How about this one? A of, let's say, double dot and 5 as fifth column. Okay, the second indices represents the number of columns. Okay, now here we use these here. Look, and I dot means row I. Okay, but n means the sum of all elements in row I. For example, n1, only 1 dot is written here. Okay, this means n1 dot means the sum of all elements in row 1. How about n2 dot? It is the sum of all elements in row 2, and so on forth. Okay, how about n.1? It's here, must not be like this. It's n.j. It's like that. It's n.j. How about n.1? This is the sum of all elements in the first column. Then n dot, let's say 3. It is the sum of all elements in column 3. And then let's say n dot 2. It's the sum of all elements in column 2. It depends on what we have in the example. If you have a matrix of 3 by 3, in the above example, we had only a 2 by 2 matrix. This is row 1, that's row 2. And this is column 1, column 2. We have only n dot 1, n dot 2, and 1 dot, and 2 dot. We have only those 4 things. What's n1 dot? n1 dot is equal to the sum of these elements in the first row. 1 plus 3 is 4. Then this one, n2 dot, is equal to 2 plus 1 is 3. Then vertically, there are columns. N dot 1. The sum of these elements, 1 plus 2 is 3. And the sum of these elements denoted by n dot 2 because they are in the second column. It's 1 plus 3 is 4. We now have these. And we need to find these in solving the question. Then we need to have n double dot. N dot dot. Sorry. If both indices are dots. This means the sum of all elements in the table, all rows and all columns, the sum of them all. Then the sum of these elements is 1 plus 3 plus 2 plus 1. Or you could just add these, which is 7. Or add these, which is still 7. Either add the sum of ni dot or find the sum of n dot j. These are n dot j's. Yan stuna kan ko karo balanta ang resulta kay ena kan kay do sino lasa stuna kan lasa risa kan on rows yan amana kob karo ياخذ امانه كوب كرو يان اي تريان كهمش بكره تيجي. Find the sum of all elements in the table. 1 plus 3 is 4 plus 2 is 6 plus 1 is 7. You get the same result in each of these. If you use any of these, you get the same results. This is n dot dot. Okay, we have n dot ni dot, n dot j, and n dot. You should know what are these. This is the sum of all of each row, the sum of elements at each row. This is the sum of elements at each column, and this is the sum of elements of all the table, all the rows and columns. Yeah, it is. We say the probability of AI intersection BJ is the probability of AI times intersection times probability of BJ. This is the rule for finding the probability of intersection of two categories. Here, we do the same as before. We need to find the expected frequencies. Those which are given here are the observed frequencies. Okay, these are in the table which is given are the observed frequencies, but we need to find the expected frequency. Expected frequency is n dot dot times probability of AI intersection BJ. Okay, EIJ as the multiplication of n double dot times probability of AI times BJ. And this equals to probability of AI times probability of BJ. We need to find probabilities of these two categories. Probability of AI and also probability of BJ. How to find them? Probability of AI is Ni over n double dot. Probability of Bj is n dot j divided by n double dot. And the probability of the intersection is the multiplication, and we get this. To find the expected frequencies, we multiply this one by n double dot. Once we multiply this by n double dot, these two cancel each other, and we get multiplying these two over n double dot. That's it. You could just use this one always. Okay? You don't need to calculate this how to get that. Just use this. وتبيس ناكام ليرو ده step كيتوا step يبرو تاجي بما يكسبله أو أكتر. Okay? وتا and the expected frequency, for example, as we have, let's say, let me write down similar to the above one, 1, 3, 2, let's say 4. Okay? If you have these frequencies, they are given. These are the observed frequencies. To find the expected frequency, what we do, let me tell you. We say this element is 1, 1. So the frequency of 1, 1 is the sum, it locates in the first row and first column. Okay? It is the sum of these elements times the sum of 8 elements divided by the total number of elements in the table. That's the rule. It is n 1 dot times n dot 1. Look at this index. First one is I, the second is j. It's E11. We always count rows first, then columns. Dividing by n double dot. We could get these easily from the table. N1 dot is the first row. The sum of elements in the first row, which is 4. This equals to 4 times. N dot 1 is the sum of elements in the first column. In the first column, the sum of these is, sorry, it's 3. Yeah. It's 3. Dividing by the total number of elements. 1 plus 3 is 4. Plus 2 is 6. Plus 4 is 10. So this is 1.2. It's 12 over 10, which is 1.2. Now, the expected frequency for E11 is 1.2. How about the expected frequency for, let's say, E22? Look, what's E22 here? What's the location of 22? Which number is in the matrix? 4, yeah. This is 4. We say, we find the sum of these elements, multiplying by the sum of these elements, dividing by the total number. Okay? Or we could say it's n2 dot times n dot 2 dividing by n dot dot. We find this one from the table. It's easy. And then we find for all. Here we have 4 elements. how many elements do you have in the table? You must find expected frequency for all of them. Here we have 4 elements. We just pick their locations, okay? 1, 1, 1, 2, 2, 1, 2, 2. We have these 4 locations. For these 4 locations, we find expected frequencies by using this rule. After finding the expected frequencies, we do the same as we did before. We say observed frequency minus expected frequency squared dividing by expected frequency. Find these all, and then find their sum, you get the result. Here we have an example I leave for next lecture, okay? And 2 dot رويا اگر جمعه سر ل 5 dot او برويا سير كأنه كارين Ij. I represents the rows. J represents the columns. Okay? When we say A32 means row 3, column 2. Here, when we say N, let's say 2 dot. N 2 dot means row 2. But if we say N dot 2, it is column 2. Okay? سيركا بلا اگر ان اجوتوا ان ناو بين بتشي ان بريتيلا ان اي دوت بريتيا لكوي اليمنت كان رويا اجا اي يجبدو بيسب اي ان دوت جي كولوم هاكو كده اي ان دوت دوت هميكو اوكي درسي دهاتون مش سباسه كانوا بس اللي بس مشاكل كباس ما كده